Started. Okay, so here were the goals for this week. By Wednesday, I wanted to teach you about sampling and distributions of samples, only that didn't quite happen. We're running a little behind. So today I'm going to teach you about samples and distributions of large samples, and probably we'll defer talking a lot about, maybe we'll start talking about models today, and then we'll start looking at how to compare whether the predictions a model makes matches the data we've observed about the real world. Announcements. Don't forget project 1 due today. Okay, so let's talk about random samples. Last time, I introduced you to the notion of deterministic samples and random samples. So sampling is a process. It's a way to get some people, let's say, from a population. And there are many ways you could select people from a population. A deterministic sampling process is one where there's no chance involved. A random sampling process is one where there's chance involved, and where the process is fully specified, so that if you wanted to, you could compute all the probabilities associated with that process. Meaning, if you wanted to know the chance that Rick and Morty were in the sample, you could compute that probability, and so on. So let's see some examples. I'm going to just go straight to some code. I am going to load in a data set. And the data set here is a data set of flight delays. The FAA publishes data about passenger flights in the US. And here they are for a period of a couple of months in 2015 for flights on United Airlines. And you can see in this table, there's like a flight number and a destination and a delay, how much each flight was delayed, like how much its takeoff was delayed in minutes. Negative numbers means it was ahead of schedule. And we have here 13,000 rows, 13,000 flights in this time period. So let's consider this is the population. This is all of the flights that happened in that time period. And suppose we wanted to take a sample from that. For instance, if you were a researcher and you wanted to know something about flight delays, one possibility is you could gather all the data on the whole population, this entire table. But that might be really laborious or tedious if the FAA didn't publish this. So another option that's sometimes used is to take a sample where we don't gather data on all the flights, but just on some of them. And then we need to process to select which flights are we going to gather data on, which flights we're going to record the delays of. So let's look first at some deterministic sampling processes. One very simple one is to pick all the flights to JFK. And I think all these flights are out of SFO. So these are SFO to JFK, San Francisco to New York City. That's deterministic. There's no chance involved. If I followed the same process again, I would get exactly the same flights. Another way would be to take the first 1,000 rows in the table. That's deterministic. If I did it again, I get exactly the same sample. Another way would be to choose some specific rows in the table, like row 34, 6321, and 1040. Also deterministic. There's no chance. If I did that again, I get the same sample. But a random sample involves chance. So for instance, here would be a random sample, an example of one kind of random sample. We might randomly choose a row in the table to start from, and then choose all the rows from there to the end, but skipping by 1,000 at a time. Kind of a crazy thing to do, but here you go. That's some set of flights. Now, if I did this again, notice how the first flight here is flight number 1717. I'm going to do it again. Now I got a different first flight in this sample. Now it's flight number 230. So this is different every time because there's some random chance involved. Notice this is like the particularly weird contrived way to choose a sample. Maybe the obvious way to choose a sample is to say, I'm going to randomly pick 10 of the flights. Maybe with replacement or without replacement. So all flights equally likely. That would be a more natural way to choose a sample. That would also be a random sampling procedure. But what I wanted to highlight to you is there are many possible ways to choose a sample that involve chance that don't all involve choosing every flight equally likely with or without replacement. Okay, so not all individuals or groups have to have an equal chance of being selected for it to count as a random sample. Though often in practice, we really do want everybody to have an equal chance of being selected. So we want not just any random sample, but one where people are equally likely to be selected. Now, I want to warn you about sampling. Sometimes in some studies you read, you may find people using what's called a sample of convenience. So for instance, if I walk down to the BART station on Center Street, and let's say I wanted to know, poll people on whether they supported the latest infrastructure bill that's being considered in the Senate. Maybe I could walk down to the BART station and ask the next 20 people who walk by, do you support the infrastructure bill? Okay, so that would be a sample. That's a sample of people, but it's known as a sample of convenience. It was just like it was convenient to get those people. It might be tempting to call that a random sample because it's kind of arbitrary who gets chosen and it's not predefined. But I want to propose that for this class, we don't consider that a random sample. And the reason is that the chances are not well specified. They're not known in advance. So we don't really have a way to know what the chances of selecting any one person are. They're unknown. We can't figure out ahead of time what's the population, what's the chance for each possible sample, for each possible group, what's the chance that that group is chosen for the sample. We don't really know what the probability model is here. And so for this class, we're going to say we don't have a random sample. Why? The reason why that's relevant is that makes it hard to assess what biases might be present in our sample if we don't know what's the probabilities of individual people being in this sample. For instance, maybe this systematically overrepresents college folks because some of you are coming into the BART station and coming into class, or maybe it systematically underrepresents you because you're all, living near campus and you don't take the BART. I don't know. Because I don't know, it's hard to know what conclusions you can draw from this. And so we're not going to consider this a random sample. Random doesn't mean no bias. Random means that the biases could be known. Okay. Good. All right. Let's talk next about distributions. We've looked at distributions when we looked at histograms. When you do random sampling, there's some distributions going on. So a distribution describes some random process. And the description is it tells you all the possible outcomes of the random process, all the possible values of this thing. Okay, so if I rolled a die, it would tell me all the possible values I could get from rolling the die. 1, 2, 3, 4, 5, or 6. It also tells me for each value, what's the probability of getting that value? What are the chances of getting that value? Okay, so the distribution has two things. It has all the possible values and has the probability for each one of those. So for a die, it would say the possible values are 1, 2, 3, 4, 5, 6. And for each one of those, the chance is 1/6. Okay, so that's called a probability distribution. If you have a probability distribution, that completely characterizes everything that's going on about the outcome of this random process. Now, where do we get a probability distribution from? There are two answers to that. In some cases, we can write down the probability distribution by thinking about it, by using mathematics, by making some assumptions. For instance, I say if I roll a die, and if we assume that die is fair, like I tell you that die is fair, then by symmetry, you know what the probability distribution is. You can work out what all of those probabilities are. They're all 1/6 because they're all equally likely. And there will be some other cases where you can work out the probabilities using math. Like, for instance, if I said roll 2 die, and then the outcome I care about is what's the sum of the numbers on the 2 die. You could, by doing some math, work out what all the possible values are. That's the numbers 2 to 12. And for each of those numbers 2 to 12, you could work out what's the probability of getting that. Like the probability of getting a 2 is 1/36. And the probability of getting a 3 is 2/36, and so on. So by doing some math, you could work out the probability distribution. All right. So that's method number 1 to get a probability distribution. The other approach is that sometimes it's very complicated to work out the math. And then a method we're going to use a lot in this class is using the computer to simulate the process. So we're going to have the computer simulate rolling these die and look at the outcome. And then we're going to have the computer do that over and over and over again. It'll be tedious for us to do, but computers do tedious things. That's what they're great at. So if we simulate the process, then what we can do is we can look at what the outcomes were and how common each one was. And that leads me to something called an empirical distribution. So an empirical distribution is as opposed to the true probability distribution. An empirical distribution, empirical means it's based on observations, it's based on data. So for instance, we might do some experiment over and over again. Like the experiment might be rolling these 2 die and observing what the sum of the numbers is. I got 7 this time. The next time I got 9, then I got 3, then I got 5. Those would be the observations. If you have a bunch of observations, you can get an empirical distribution from them. The empirical distribution says, here are all the values that were observed. And for each value, how often did it occur? The proportion of times that value occurred. So notice how similar this is to a probability distribution. It's a bunch of values and a bunch of chances, numbers between 0 and 1. For an empirical distribution, it's a bunch of values and a bunch of proportions. Now, if you rolled a fair die 100 times and you observed all the outcomes and you wrote them down, you'd probably find that you'd seen all the numbers 1 through 6. And how often did you see each of the numbers appear? How often did the number 1 appear? Maybe not exactly 1/6 of the time, but probably the proportion would be kind of close to 1/6. So this motivates why we look at empirical distribution. If you don't know how to compute the probability distribution using math, then what you can do is you can simulate, you can gather the empirical distribution, and then use that as your estimate or an approximation of what the probability distribution is. Okay. Let's see that in some code. I just talked a long time. So let's look at rolling a fair die. Okay. So here I have a table with all the possible outcomes. The number is 1 through 6. And I'm going to imagine that I roll a fair die 6 times. Sorry, 10 times. 10 times. So a way you can do that, if you have all the possible outcomes in a table, is you can use the sample operation on this table. And what the sample operation does is it repeats 10 times. See, this argument here says how many times to repeat. Repeat 10 times, and in each repetition, in each round, what we're going to do, what sample is going to do, sorry about that. Sample is going to pick a random row from the table and append it to the output. Okay, so we've got 10 random rows from the original table. And this is what's called with replacement. So we pick one of these rows randomly, and then we pick another one. After we picked a row, we put it back in there and we pick another one. So we might get the same one twice. So you can see this is effectively simulating rolling a die 10 times, and here are the outcomes of those 10 dice rolls. What if I wanted to sample 2 dice at a time? One way would be to create a table of all the possible outcomes you could get from rolling 2 dice. So that'd be a bigger table now, right? Because there are 36 possible outcomes. And so you would have a table with 36 possibilities in it. And then you would call the sample operation on that table, like 10 times. Okay. So let's look at first at the probability distribution. This is the probability distribution. The display looks a little funny, but what we can see is that each number 1 through 6 has the same chance of being selected. Now, you notice how this histogram didn't really turn out right. They didn't have the bins that I wanted. So I'm going to manually specify some bins so that this turns out right. This gave me 10 bins, and I really want 6 bins. So let's redo that with some manually specified bins. And now I'm happier. So now we can see this is the probability distribution. It shows the possible values. It's a visualization of the probability distribution. The possible values are 1 through 6. And the probability of each happening is 1/6, 16.6%. So now let's do the same thing, but for our sample. Okay, so we're going to construct a sample of 10 random dice rolls. And then I'm going to visualize the proportion of times each for each outcome. This is now an empirical distribution because it's a distribution of a bunch of observations of a distribution of a sample. And so you can see that in this sample where I rolled the die 10 times, a 4 and a 6 came up 20% of the time, a 5 came up 30% of the time, and the others came up only 10% of the time. Okay. Now, I want you to notice that this was a random sample. So if I did it again, I have a new random sample. I've rolled the die 10 more times. Now I might get a different empirical distribution because I got a different set of outcomes. Okay. So that's what the empirical distribution might look like. Let's try the same thing, but with more rolls of the dice. You notice that there's a big difference between the probability distribution and the empirical distribution. The probability distribution, every number was equally likely, all had a 16% chance of occurring. In this sample, some rolls occurred a lot more than 16% and some quite a bit less than 16%. That's because our sample size was so small. So let's look at what happens with a larger sample. With a larger sample, we get an empirical distribution that looks like this. Now I rolled the die 1,000 times and counted what proportion of times it came up a 1, and the answer was a little bit close to 18%. So that's a little higher than the 16.6% of the probability distribution, but not too much higher, and so on for each of these bars. What if I chose an even larger sample? Now I'm going to roll the die 100,000 times. It'll take the computer a little while to do that. It's got 100,000 observations and then computes the empirical distribution. How many times was a 1 observed in that random sample of 100,000? Is this closer to 16.6% than the previous empirical distributions, or is it further? Closer. Yes. Is this empirical distribution when I had a sample of 100,000? Would you say that's similar to the probability distribution or very different? Yeah, it's really similar. What did the probability distribution look like? The probability distribution looked like this. They were all at exactly 16.6%, all at the same height. This is not quite all at the same height, but they're really close. They're not all at exactly 16.6%, but they're really close. Okay, so remember that. There's a reason why we like large samples. But what this hints at here is that if you don't know how to compute the probability distribution, what you can do is you can simulate the experiment many times to get a large sample, find the empirical distribution from the results of that simulation. And now the empirical distribution will be very similar to the probability distribution. Okay, so this is kind of an alternate way to using math. In this case, we knew what the probability distribution was, so we didn't need to go through all that rigmarole. And I showed it to you primarily so you could get some confidence that the empirical distribution resembles the theoretical probability distribution. But there will be times when we don't know how to compute the probability distribution, and all we can do is simulate. That's okay, because as we're seeing here, as long as you have a large enough size sample, a large enough number of repetitions, the empirical distribution should be similar to the probability distribution. Will the empirical distribution ever be perfect? Probably not. It could happen by chance that exactly perfect, but typically it won't be. That's okay. If you think about me getting out a ruler to measure the length of my sofa, or a tape measure, am I ever going to get that measurement exactly perfect? Probably not. Was it 43 1/8 or was it 43 2/8? Okay, so not much in life is perfect. If so, can I calculate how many trials will give me a given level of accuracy? Yes, yes, hold on to that, hold on to that. Stay with that. We will get to that in this course, but just not yet. But absolutely, love it. How exactly does the computer actually randomize? Let me give you a story that's not really accurate, but it's close enough. You could imagine that when you boot your computer, it has a clock in there. And when you start up your computer, it looks at the clock, and that clock is accurate down to the nanoseconds. And it looks at the nanoseconds, the last digit. And if the last digit was a 3, then it, uses that last digit to help generate some randomness. And then it uses some algorithm to start with some little bit of randomness and then generate new numbers from that. And there's a study, there's a field of computer science called pseudo-random number generation that studies how to do that. Some modern chips actually have random number generators built into the chip. So they have a little circuit that the electronics are designed very carefully so that it's equally likely whether you get a high voltage or a low voltage. And so it measures that voltage repeatedly many times when you want a random number, and uses that to select a number. You could think of it as like a 20 questions. Like first it checks whether there's low voltage or high voltage, and use that to decide whether the number should be above a half or below a half. And then let's say it says below a half, then it checks it again, decides whether it's going to be above a quarter or below a quarter, and so on. All right. Next thing I want to show you. I want to show you how to draw in Python some code we've given you to sample from a categorical distribution if you know the probability distribution. Sometimes we'll know it, sometimes we won't. But let's suppose you do know it and we have a categorical distribution. Then there's an operation we've given you called sample proportions, which you can use for that. And it has 2 arguments. One is the sample size, how many times you should repeatedly draw a random value. And the second is the distribution of the population. So you think of this as we're drawing from some population, and we want to know the distribution of that. So it's a categorical thing. So the distribution will be represented by an array that has the probability of each of the possible values. Okay, and this is going to sample from that distribution, meaning according to those probabilities. It's going to do this sample size many times, and then put all those results in an array. All right, so let me show you an example of this code. Let's take an example I hope this is not too deep or gloomy for you. I looked up some statistics and found that in any given year, about 10% of US adults suffer from a depressive illness. So let's think of this as a categorical distribution for each person. Either they suffered from a depressive illness at least once this year, or they didn't. Then in the US population of all US adults, we know that 90% didn't and 10% did. So the distribution, the probability distribution for this categorical variable has two possible outcomes, didn't or did. And for each of those, we have a probability, 90% chance didn't, 10% chance of did. So if you were to randomly select a person from the population of US adults, there'd be a 90% chance that the outcome for them would be didn't, and a 10% chance that the outcome would be did. Now, I'm going to put that into an array. So we can look here at the array that has the probabilities for the probability distribution. And then let's imagine you have 100 friends, 100 people you interact with every so often socially that you know. And let's, for the moment, assume or pretend as though those 100 people behave for purpose of mental illness like you had drawn randomly 100 people at random from the US population. So your first friend was like sampled at random from the population of US adults, all of them being equally likely. And then your second person, we sample another person from all US adults, all equally likely, and so on. And then let's look at what the implications are for your friends. Now that assumption, I should say, is really dubious. That's not how people make friendships in real life. So this is a thought experiment, not something to be taken too seriously. Then we can use the sample proportions to ask the computer to simulate this process of drawing 100 random friends, looking at which of them, for each of them, the outcome of this categorical variable did have a depressive illness or didn't, and then compute for us the empirical distribution of that sample. And for this example here, we got 88% of your friends in this sample didn't, and 12% did. So I thought this was kind of eye-opening. If I know 100 people, maybe I don't know them that well, maybe 12 of them has suffered from some depressive illness this year. Wow. And this is random. So if I did it again, I would get a new sample and a different empirical distribution. You can notice how the empirical distribution is kind of similar to the probability distribution, but it's not exactly the same because of the random chance of those 100 people. You might just happen to get more that had a depressive illness or fewer that had a depressive illness. Okay, now I was getting at before large random samples. We've been getting at random samples, and we saw when we were looking at empirical distributions and probability distributions that the larger samples had an empirical distribution that more closely resembled the probability distribution. There is a theorem in statistics called the law of averages, or the law of large numbers, which formalizes what we were seeing today. It says what we are seeing today is not an accident. It's in fact something that always happens. So what this says is if you have a random experiment that involves some randomness, some chances, and you repeat it many times, the same experiment each time, you repeat it. So let me give you a working example you could use for what I mean by experiment. That might be rolling a fair die and writing down what number you got. So if you repeat that many times, independently and under the same conditions, so that means each time I do it the same way, with the same conditions, the outcomes of the past stuff doesn't affect what I do on the next one, then the proportion of times that some event occurs, you could think of the event being like, I got a 5 on the top. the proportion of times that occurs gets closer to the theoretical probability of the event. As I repeat it more times. Okay, so let's unpack that. That was a lot. Suppose that I have a fair die and I roll it. Maybe I roll it 10 times. And I count how many times I got a 5. The theoretical probability of getting a 5 on any one roll is 1/6, exactly 1/6. If I do this process 10 times and count how many 5s I got, particular, I count the proportion of rolls that came out a 5, that number might not be exactly a 6. It might be 10%, or it might be 20%, or it might be 30%. I could do the same thing with 100 rolls. Now it might be 15% or 18%. What the law of averages is saying is the larger the sample, the closer those things will be. The theoretical probability 1/6. The observed proportion 20%. 16% and 20%, kind of close. The larger the sample, the closer those numbers will be. So in other words, the better an estimate the empirical distribution will be of the true probability distribution. Okay, so that's a really complicated way of saying large samples are better. But it helps you say in what way they're better. What's the minimum number of trials that would fulfill the condition of the law of large numbers? There is no minimum. This is not about a minimum. The law of large numbers is not a black and white. It doesn't say small sample, no good, large sample, perfect. What it says is the larger your sample, the better it gets, the more accurate it gets. There will still be some error, but the amount of error reduces as you increase the sample size. Okay, so the law of averages is really, you could think of as a thought experiment of like, if we could do this just a ridiculously large number of repetitions, then the more repetitions we did as we kept doing it, we'd be getting closer and closer to the true number. We might not ever get there. Yeah. Proof, if you want to see the proof, take Stat 88. You can take statistics courses where these things are formally proven using mathematics. But for this course, we're trying to spare you so that you don't have to have any math background. So you just got to trust me. Or take Stat 88, and then you don't have to trust me. Okay, so what this means about empirical distributions is that if the sample size is large, then the empirical distribution of a sample is chosen uniformly at random from a population. Uniformly means everybody is equally likely to be selected. Then the empirical distribution resembles the distribution of the population in a large, usually with high probability. It's likely that the empirical distribution resembles the distribution of the population. This is another fundamental fact. It follows from the law of averages. This is, for instance, the fact that underlies why statistical polling works, why you can pick 1,000 random Americans and ask them who they're going to vote for in the next presidential vote. And that will give you a pretty good estimate of the proportion of people in the total population of eligible voters, how they'll vote. It's because when we call 1,000 random voters, that's like getting the empirical distribution of a random sample of 1,000 people chosen from the population. And that's a good estimate of the actual distribution of the entire population. Okay. Let's look at some more code. All right. So let's see this happen with our flights data set. I am going to load in again the database of all these United flights. And since we have all the data, we can look at the distribution of the population. Here, the population is all those flights in that time period. And we can look at the distribution of the delay. Some of them were more delayed, some of them were less delayed. You can see here, most flights really didn't experience any significant delay, but there's a handful that had a delay of an hour or longer. And in fact, actually, you can't see it on this graph because the bar is so low, but there was even one that had a delay that was, I think, somewhere around 200 minutes. So like 3 hours sitting on the tarmac waiting to take off. Ouch. Okay, that's the distribution of the population. Let's try choosing a random sample. Let's try choosing a sample of 10 flights chosen at random, all equally likely. And then let's look at the empirical distribution of the delays of those 10 random flights. And here's what it looks like. Does the shape of this look anything like the distribution of the population? Maybe a little bit. In really crude terms, it's kind of high on the left and then lower on the right, but not really. What if I chose 1,000 flights? If I chose a random sample of 1,000 random flights, chosen uniformly at random from the population, and then I look at the delays in my random sample, the distribution of delays in the sample looks like this. So this is the empirical distribution based on the observations from my sample. And now you can see the shape of this looks a lot like the shape of the overall population. In fact, it's really hard to tell them apart. Okay, so what are the implications? If you wanted to study flight delays and you didn't have a way to get the full data set for all flights, you could instead choose a random sample of 1,000 flights and get the delays for those. And that would be basically good enough because it would have essentially the same distribution. So for instance, maybe you're a researcher, you could try to get the data for all flights by sending out assistants to the airport to write down for every flight that takes off out of SFO how long it was delayed over a multiple month period. And that sounds painful. Or you could send out assistants to just write that down for a random sample of the flights, and maybe that would be easier. So yes, the bigger the sample, the more similar this empirical distribution will look like the real distribution of the population. Let me pause here for questions. You have to specify with replacement equals false. These samples by default are with replacement, which means that it might choose the same flight twice in the sample. If you don't want that to happen, then you need to tell it without replacement. And the way you can tell the sample procedure that I want you to sample without replacement is to add an extra additional option that indicates that you don't want it to use with replacement. So let's see how to do that. And in this case, you can see that it didn't really matter that much to the ultimate distribution about whether I sampled with replacement or without replacement. There are some settings where it will matter. What's the importance of having or not having replacement? If we're doing simulations or we're doing mathematics, we want to make sure that the simulation or the math we're doing matches what's actually happening in the real world. If I'm rolling a fair die, I might get the same number twice. So it's important that our simulation also take into account that we could get the same number twice. If I'm doing a poll of likely voters and I call them up, you could do that in a way that ensures that you don't pick the same person twice. And then that would be without replacement. And so if we're doing simulations, we probably want our simulations to match the procedures that we're actually using when we do the poll. Okay, So next, I want to talk about the next concept, which is the notion of a statistic. You may have heard of the field of statistics. Here's where that field got its name. A statistic is a it's like a variable, a way of getting a number. Okay, so the field of statistical inference or inference is about making conclusions about the real world based on data in random samples. So like making a conclusion about how the population of eligible voters are going to vote in the next election based on a random sample, based on people who responded to your poll. That's statistical inference. So we might, for instance, try to guess the value of an unknown number using the observations in our random sample. The unknown number might be, out of all eligible voters, what fraction will vote for Joe Smith? So in the field of inference, we're creating an estimate of this unknown quantity. There's some quantity about the population at large, but we can't directly observe it. We don't have all the data of what everyone in the US is going to do in the next election. So we get some observations and then we form an estimate of that unknown quantity. This unknown quantity is fixed. It's some truth about the population. There's no randomness there for our purposes. The randomness comes from when we randomly choose a sample. Who is going to be in the sample? Okay. The sample depends on the random choices we made of who's going to be in the sample. Our estimate depends on the sample. So our estimate is also going to be random. It's also going to depend on this random sample. If I got a new sample, I would get a different estimate maybe, even though the underlying quantity we're trying to estimate is fixed in the same. Okay, so we have some language, some names for this. The parameter is this thing we're trying to estimate. A parameter is a number that's associated with a population. So for instance, it might be the fraction of all eligible voters who are going to vote for Joe Smith. Or it might be among all employees employed by the city of San Francisco, what is their median salary? So that's a parameter. It's a single number about the population. If you knew all the data about everyone in the population, you would be able to compute the parameter. A statistic is also a number, but now it's associated with a sample. A statistic is a number that's calculated from the sample. Usually, we're going to use the statistic as an estimate of the parameter. So it's very common that we don't have all the data for the full population. We only have data from a random sample. We have observations from a sample. We're going to then try to infer something about the population based on the sample. So we're going to try to estimate the parameter based on the sample, and the statistic is something we compute from the sample that we can use as our estimate of the parameter. Why do we have any chance of doing this? That's because of the law of averages. The law of averages tells us that the sample somehow resembles the population, resembles in the sense of distribution. So computing something from the sample should give you a reasonable guess at what that something is about the population. Okay, let's see an example, because that's a lot of words. It's pretty conceptual. Let's look at a concrete example. Start with a parameter of the population. Let's take the set of all flights and compute the median delay of all flights. In this case, it's 2 minutes. If I had all the data, I could compute the median delay was 2 minutes. So half of the flights have a delay of 2 minutes or less, and half of them have a delay of more than 2 minutes. Alternatively, I could compute a random sample of 10 randomly chosen flights, and then compute the median delay of those flights in the sample. That would be called a statistic because it depends on the sample. There is a random sample. I chose a random sample, and of the flights in that sample, the median delay was 7 minutes. I could get another sample from another 10 flights and compute the median of those. And this time, the median of that second sample was 0.5 minutes. So you can see the statistic depends on the sample. Even though the parameter hasn't changed, the set of overall flights in the population hasn't changed. It's still 2 minutes. So in one of these, I just happened to, in the first sample, I just happened to choose more flights that were more delayed. And in the second sample, I happened to choose a little bit fewer of them just because of that was how the random chances worked out. It was kind of a coincidence. I could choose a larger sample and get the statistic based on that. So I could choose 100 random flights and then compute the median delay of those sampled flights. And now the answer is 4.5. I could do an even larger one. Here's another statistic. 2 minutes. Notice how that was a little bit closer to the true population parameter. So now let's talk about the distributions of a statistic. The values of a statistic might vary based on the random chances. That means it's a random quantity. So that means it has a distribution. Okay. So a statistic has a distribution. That means you can work out what are all the possible values that you might get for that statistic and what's the probability of each of those values. That distribution is called the probability distribution of the statistic, or sometimes called the sampling distribution of the statistic. Okay. It might be really tricky to calculate. What's the distribution of the median of 10 randomly sampled flights? Oh man, don't sit down to try to do the math on what that distribution is, because it's a beast to do the math. So we're in a situation where it's hard to use math to get the probability distribution. So we're going to use our alternate procedure that I highlighted earlier today. Instead, if we want to know what that distribution looks like, we're going to simulate and get an empirical distribution and rely on the law of averages for our confidence that this simulated empirical distribution will resemble the true probability distribution of the statistic. All right, so the empirical distribution of a statistic is obtained by simulating the process of random sampling, getting a statistic from that random sample, doing that many times. Each time you got a different value for the statistic, and then forming the empirical distribution of that, like what were all the observed values you saw and what was the proportion of times that each occurred. And by the law of average, this will be a good approximation to the probability distribution of the statistic if we do enough simulations. So notice there's two kinds of sampling here. There's a sampling we do to get a sample and then compute a statistic from that. And then we're repeating that many times, which is in turn kind of like a second kind of sampling. So it's kind of like we're doing a sampling of sampling process. So I hope that's not confusing. So we'll do an example here. Let's write a function that takes a random sample from these flights and computes the statistic, the median delay of the flights in the sample. We could do that for a sample of 10 random flights. And in this one, the average delay was -2 minutes. Then I'm going to repeat this. So how do I, when I want to do something many times, when I want to do a simulation many times, remember the procedure? I create an empty array, and then many times what I do a for loop. In this case, I'm going to do it 2,000 times. In each iteration of the loop, I simulate the process, and then I append that to my array. So I'm doing 2,000 times, choose a random sample, compute the statistic, the median delay of the sample, and add that to the array. So now I've got an array here with 2,000 numbers in it. Those are the 2,000 observed values of the statistic in these 2,000 random samples. And they range, there's a whole range of values here. If I then put those in a table, I can visualize the histogram. And this is what the histogram looks like. This is the distribution of the statistic. So the median, the sample median, the median of the flights in our sample. Now, there's something really interesting happening here. This tells you about the range of values you might get for our estimate of the population parameter. Remember, the median in the population is 2 minutes. This is our estimate. So our estimate is not always going to be 2 minutes. Sometimes it's going to be too low. Sometimes it's going to be too high. But this tells me about how accurate of an estimate we have. You can see that it's fairly common for our estimate to be too high by maybe 5 or 10 minutes. But it's very rare for estimate to be too high by 30 minutes. So this helps me get a sense of how accurate an estimate I get from this sample statistic. All right, there's more to say about this, but I'm going to stop here. I want to make a brief announcement. There's a homework being released today. The book has a new section that will help you with this. Please take a look at that part, in particular, section 10.5 of the textbook. Have a great weekend. Don't forget to turn in your project 1. Bye, everyone.